Hello, so we're going to talk a little bit about some basic concepts of probability. So one of the basic concepts is that we look at the what is called the union rule. Now, the union rule can be kind of visualized by using a Venn diagram. So normally when we use a Venn diagram, we say that there's a universal set in discussion. And then typically we might have, for example, that you have a set A and then you have a set B. So we'll just label this as set A and this as set B. Now a union means that you have that the region that would be shaded is everything within the two sets. That includes the intersection as well, but be careful because you might have that the entire Venn diagram has that the two sets do not have anything in common. So what we want to do here is just figure out, like, for example, like what is the probability of the two events, like with that we're saying like what's the probability that they both do occur. So let's go ahead and figure out, for example, like if we had the probability of A. The probability of A is really just the count of A divided by the count of S, which is the sample space, or we could put the universal set if you want. The probability of B would have to be the count of B divided by the count of S. Now we do have this little intersection right here, so that means that we have to go ahead and just put the intersection. So the probability of A intersect B by definition is the count of A and the count of B divided by the count of S. So my goal here is that I want to figure out like what's the probability of the union of the two events. So the probability of the union of the two events, and we say like the probability of A or B, is equal to the probability of A plus the probability of B. Now if I scroll back up and I look at my Venn diagram, I'll notice that if I added both the probabilities of A and B respectively, that I would have counted twice the intersection. So what that means is that I need to subtract it from our sum. So we have the probability of A intersect B that has to get subtracted. So this is going to give you your formula for finding the probability of two events if they have something in common. Now, keep in mind that if they do not have anything in common, for instance, we'll just put like a little note here. If the probability of A intersect B is equal to 0, then that means that it's just the probability of A plus the probability of B. So let me just explain what I mean by that. So if you have that a set of two events are what we say mutually exclusive, what that really means is that they actually have nothing in common. So that means that the intersection of A and B is empty. But if you're looking at the count of an empty set, that's going to be 0. So what that means is that the probability of A intersect B is 0. So you have that those two sets are disjoint, meaning that they have that the union rule would specify that it's just going to be the sum of the two sets. Now, let's say, for example, that we want to find a certain probability, So, um, let's say that we do the example of rolling a pair of dice. So we'll just say that a pair of dice is rolled. Okay, so we want to find the probability the first die we'll just say lands on 2, or the sum of the dice, is, we'll just say 5. Okay, so this means that we have 2 events that we need to look at, and that's going to be determined by just kind of like writing out the different outcomes. So we have 1, 2, 3, 4, 5, and 6, and that only will determine the first. Okay, so we need to write this out, and it helps to, kind of make like a little grid, or if you use your textbook, there's actually a diagram in the textbook. So let me just label this as the first die, and we'll label this as the second die. Now, I'm going to use like little tick marks instead of doing like 2-1, 2-2, and so on. So I'm going to use a different, well, let's use a different color. So the first die is a 2, is this 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, and 2, 6. But note that you wanted to find when the sum is a 5. So the sum is a 5 is right here, 1, 4. Okay, and then we have 2, 3. Now let's just actually just circle this instead. Okay, so 2, 3, and then we have 3, 2, and then we have 4, 1. Now notice that that's all of them. So we have that that's going to be just those events. So let's go ahead and see this. So, and we can probably just write it in this little space right here. Why not? So you have that the probability that the first die is a 2, that's equal to, well, you have that essentially that there's 6 different outcomes, but out of 36. The next probability that we can find is the probability that the sum is a 5, which is just these 4 different outcomes. So we have that that's going to be 4 out of 36. However, we need to find how many outcomes that are both the first die is a 2, and that the sum is a 5. Okay, so let's just move this up a little bit because we don't need the diagram anymore. So the first die is a 2 and a 5. Well, we only have that the only outcome of which that it's a 2 and that adds up to 5 is 2 comma 3. So that's going to be 1 out of 36. So according to the union rule, it tells me that I just need to take the probabilities respectively. And since I don't want to write this all over again, I'm just going to label this as E and this as F. And that way I can just put E intersect F. what you'll find is that most mathematicians try to find shortcuts. So probability of f, um, and yeah, I'll just leave that, minus the probability of E and F. Okay, so this is going to equal to 6 over 36 plus 4 over 36 minus 1 out of 36. Now, I left it like this so that you can easily just add this up. So we have that that's going to be 9 over 36, not 16. I don't know why I wrote 16, but we'll just put the correct number. So that's going to be 9 out of 36. But doesn't that just equal to 1/4? Which means that the answer, if you write it in decimal, is 0.25. So the answer to this question is 0.25. Okay. Now, we do have another rule that is used when it comes to probabilities. Okay, so the other rule that we have when it comes to a probability um, is what we call the complement rule. Now, the complement rule is really just best if you've kind of like visualized it using the Venn diagram. So we have that our universal set is usually like that. And if we just draw our set A, and I'll just label it like this is going to be A. Well, you have that the shaded region that you would have would be everything outside of A if we were looking at the complement. And if you look back in the introduction to sets, you'll see that the complement rule was defined similar to how we're going to define the complement rule. So for instance, if we go ahead and we try to see that we want to find the probability of a complement rule, well, the thing is that when we look at this, is that we have to realize that, well, the probability of the complement of A has to equal to the count of the complement of A divided by the, not the probability just yet, but the count of the sample space or the universal set. So the way that we can do this is that we have to think of it like this. How do you get the complement or the count of A complement? So that's going to be, you take the count of the whole sample space minus the count of A, and all of this is divided by the count of the sample space. But interestingly enough, if you actually simplify this a little bit more, where you take the count of the sample space divided by the count of the sample space minus the count of A divided by the count of the sample space, this actually reduces to 1 minus the probability of A. Okay, so that was some bit of work just to figure out that, oh, you just have to kind of subtract it from the other. So like we have the probability of A complement is equal to 1 minus the probability of A. So we have that this is our formula that we're going to use for finding the complement of any event. Well, the probability. So, you know, one easy way to kind of understand this is that you can kind of think about it like this. Like, what if a coin was flipped? and you had that the probability of heads is 1/2. Well, the probability that it doesn't land on heads, which in this case would be tails, is going to be 1 minus 1/2, which is still just 1/2. But, what if we were to say, for example, the probability that a die lands on 2? Well, I know that it's 1/6, but what if I want to look at the probability that it doesn't land on 2? Then in that case, that would be 1 minus 1/6, which is just 5/6. Okay, so that means that essentially if I know the probability of the event occurring, then that means that I know the probability of it not occurring, if that makes sense. So what we can do is look at an example of when we use the probability, the, the complement rule. So, uh, ah, I know a good example. So let's say that we have that there are 3 green marbles, and that there are 2 red marbles, and let's say that there are 4 yellow, and then let's say that you have that there are 6 blue marbles. So let's try to find the probability we'll say it like this: find the probability of not selecting a blue marble. Okay, so the reason that I'm doing it like this is because I want to show you that, what if we didn't know the probability to begin with? Then we would have to find that first. So the easiest way to approach this problem is to think of what's the total outcomes in this case. So we should probably say that the assumption is that a single marble will be selected at random. So that means that you have to think of, well, what number of options are available? Well, you have 3 plus 2 plus 4 plus 6, which is equal to 15. So next I need to figure out like what's the count of selecting a blue. Well, the count of selecting a blue is 6. So the next thing that I need to do is find the probability of finding a blue marble. So that's going to be basically just the 6 out of the 15. So next we'll just do the probability that we don't select a blue. So we'll just say not blue. Well, that's just going to be 1 minus 6 out of 15. But if we reduce this even further, that's going to be 9 out of 15. Okay, but while that is the solution, you can have that this can be reduced even further. This reduces as 3/5. So that gives us 3/5. which is equal to 0.60. Now, I would say that it actually may have been a little easier if you would have just counted how many are not blue. So 3 plus 2 plus 4, which is 9, and then out of the 15, so that gives you 9/15ths. But that's the exact same thing. So more or less, this is just really a matter of preference if you prefer to use the formula where you have the probability of an event complement is 1 minus the probability of that event. Now, one thing that you should note is that the probability of the complement plus the probability of the event A must always equal to 1, no matter what. So if I did a survey on how many people own a dog and I found out that 67% own a dog, then naturally I would know that those that do not is 33%. So why is that? Because it has to equal to 1 at all times.